Hello. Finally, I think you can hear me, right? Thank you. Yeah. I'm really sorry about the delay to all the participants. So this portal was something new, but anyway, we are there. Just kidding. Thank you. Sure, sure. Yeah. I'm really sorry. Please go ahead.
So can I go, sir?
Yeah, ma'am. Please go ahead.
Yes, sir. Good morning to one and all present here. This is R. Jahnavi, Assistant Professor of ECE Department at SRIT Anantapur. It's my great privilege to introduce Kondareddy Mopuri Garu for 1 week online HTTP on machine learning, recent trends and applications phase 2, sponsored by AICTE. Kondareddy Mopuri Garu is visiting faculty member for Department of Computer Science at Indian Institute of Technology, Tirupati. He working as machine learning computer vision and he held a postal doctoral position at the Visual Computing Group VICO, led by Dr. Haken Bilen at University of Edinburgh. He did his PhD at Indian Institute of Science, Bangalore, where he was advised by Professor R. Venkatesh Babu. His thesis won IUPRAI Best Doctoral Dissertation Award and SPCOM Best Doctoral Dissertation Award for year 2018. He did his master's at the Indian Institute of Technology, Gorakhpur. My team and I are so lucky to have you as a resource person like you participating in lecture. Your presence and experience has to give us more information for us, sir. Thank you for having you on the session, sir.
Yeah. Thank you, ma'am. Thanks for a kind introduction. So yeah, I think because we have lost some time, if you allow, I can start. With the lecture.
Yes, sir, you can start, sir.
Yeah. It seems I need a permission from the organizer. Okay. All right. This is still something new. Okay. Anyway. All right. So yeah, I know the program is to discuss a little more advanced topics on machine learning and related areas. But somehow I feel, statistical learning, particularly linear regression and logistic regression, although these are the first modules that will be taught in any machine learning course, these are not very, very, although they are basic, they need not be, underrated. So I personally feel, these powerful techniques need to be very well understood by all the practitioners in machine learning and AI, so that they will understand whatever new or latest technologies that are there, so that it will be as we can see, it's a jumping off point to into the ocean of machine learning. So I just wanted to discuss and introduce first, and then discuss the power of these simple techniques like linear regression and logistic regression. So in this session we'll try to focus our energy on linear regression. So basically some of you might already know it, but let me just give a statistical picture of it. So we all know it is a simple supervised approach, but if you don't know, it's also fine. This is, I want to really introduce this topic. So linear regression is one of the simple supervised approach where you have both the data and labels associated, and you're trying to learn uh, a function that maps the input to the labels. Here, labels are quantitative responses. So particularly this technique is useful for predicting quantitative responses. That means as opposed to a categorical response of class 1, class 2, class 3, which is a classification problem, here the quantity we are predicting is a continuous response. For example, temperature. Temperature can be a real quantity like 12.3, 35.7, all these things, right? So this supervised technique is used to predict these quantitative responses. As I said, this is a supervised technique where you have both the input and the label, where the training data and testing data will be in that well-known picture. All right. So also, this is one of the widely used statistical learning tool. Mostly, yeah, in industry, it is one of the best tool people try to use. And this is strong baseline also. People, when they start attempting a problem where they have data and they want to come up with a solution, they start immediately with the simple things like linear regression, and these kind of also tells you what is the bottom, and what is the expected performances that we are aiming at, all these things. And in most cases, at least in the industry, like a good percentage of the problems will be solved using linear regression. So that is why I feel it is a little underrated in academia, not in industry, definitely. And also, it helps in great deal in understanding the advanced techniques. So it clearly is a jumping off point into the world of machine learning. And if you do some advanced topics and courses in machine learning, you will be able to see that some of these recent techniques are either extensions or more generalizations of this linear regression. So the funda is very clear. Intuitions are taken forward, but with more capacity added, with more sophistication added, so that all of this makes linear regression a very important tool. So everybody should clearly understand it, and be able to use it uh, quickly, so that later techniques will always try to compare its performance with linear regression. Sorry. All right, so I just wanted to give applications. Although I said it is one of the most widely used tools in industry in machine learning. So for example, a lot of websites and companies generate insights on consumer behavior, particularly e-commerce websites like Amazon, Flipkart, and all that. So all those category of companies actually use a lot of regression models to understand insights, um, and understand the behavior, consumer behavior, how these customers are behaving, how the buying patterns have been, how the trends, all those things have been over time, and predict also for the future. And for understanding business and factors influencing the company's profits and revenues, right? So basically, it is kind of a quick tool that people in business apply these kind of techniques on different factors that influence the company's future in terms of the revenue. Also, it evaluates trends and makes estimates for the behavior of the business or the sales forecasts, etc. So this is very important. It has to evaluate the trends and make estimates, so that the leaders of the business make appropriate plans, and logistics will be arranged in order to cope up with the changing trends, and also to increase or maximize the profits. All right. So throughout we'll have a running example, just to make sure we will relate. So it is always a good idea, particularly in machine learning, to have an example with which we will be able to relate our conceptual discussions, so that things get a little hands-on, where you see what is happening in a tangible fashion, right? So that is why we kind of have one example, where the example is to estimate the sales. The advertising, the companies, we all know, right? The companies use advertising to popularize among the people, so that people buy the product and the company earns profits, right? So advertising is a very impactful medium to get the product into the people. So this is a widely used test case. That's why I picked it. So there are three different ways the company looked at for advertising, which is yeah, using TV to display the ads in a small video format, let's say, and radio. For example, FM radios, we all know a lot of advertisements will be um, for telecasted in radio also. Newspaper is another medium where you present ads of the company introducing the product. So all of them will help increasing the sales. So the y-axis is, so this is data collected from the company. This is actual data. I forgot the company and the product, but this is a meaningful data where x-axis tells you in thousands of dollars spent in these mediums, respective mediums, and y-axis also in thousands of quantities. So whatever the product is, 10,000, 15,000, 20,000, 25,000, and so on. So this is a plot which tells you how many of the products have been sold after spending how much on TV advertising, radio advertising, and newspaper advertising. So yeah, this we can clearly see roughly when you increase advertising, the money spent on advertising, most often you see the products will be more sold, right? So so not only in this particular problem, so as a technician, as a practitioner of machine learning, it is always a good practice to visualize data to whatever extent it is possible. We have to eyeball the data, so it will tell us a lot of stuff. So you need to, so without even doing any machine learning, we can say, right? So as the money spent on TV advertising is increased, the sales increased. So this is also one of the important inferences. However obvious it may be, however small the effect of that may be, the first step every machine learning practitioner has to do is visualize the data and try to see how the data is organized, or how what the data is telling without applying any techniques on it. Because in most of the cases, people it happened for real actually. So for example, when I was doing my postdoc in UK, so there were technical discussions where I happened to have a discussion with a prof from US. So what he said is to his PhD students, I asked, basically I also want to become a professor and want to guide some PhD. So I asked him, so sir, what is the first step you do when you get a PhD student? How you give him a problem, or once you give a problem, how do you approach guiding? So he says, I asked, I mean, most of his PhD students, he asked his students to, he'll give a data set, particularly in computer vision, like object recognition, detection, segmentation. These are some of the problems, right? Face recognition, all that. So he works in computer vision. He said me that he'll give the data set and ask the student to spend, at least 2 to 3 weeks going through the images, right? So there will be thousands of images. Obviously, if it is ImageNet sort of a data, 1,000 classes will be there and millions of data will be there, images, right? So I was really surprised. Like, is it possible to actually go through all thousands of data? Maybe if it is small, yes, but if it is big, we cannot really go through. Like, what was the objective? What do you expect the student to learn out of this experience? And he said, see, we are the ultimate intelligent beings, right? Machines, we are training them to do our jobs. So they can't really, perform some of the tasks that are linked to intelligence. So obviously, so to whatever possible extent, we have to attempt the problem and try to understand and read what the patterns are, how we can approach to solve the problem and all that. So I clearly remember, until then I was really surprised, um, going through the data, which is sometimes huge, right? But anyway, for problems like this, it is very easy, right? So if you don't display, if the data is given to you in Excel sheets or CSV files, and if you don't open them and visualize them in the plots, obviously we cannot really see this kind of trends, right? This is very easy, this problem, because we are experienced with advertising and we believe that, with increasing advertising, more products will be sold. That is okay. But there will be a lot of unobvious things which will be clear only after visualizing the data. So I urge you to start, if you are, if at all you work with machine learning problems, try to spend visualizing and looking at the data, going through and see some of the trends yourselves. And then it is easy to use the suitable techniques, machine learning techniques, to solve the problem. All right, let's get back. So this is what the running example is that we are going to take through this lecture. All right, so on the basis of this data, actually, as a statistician or a machine learning practitioner, you will be asked to make a marketing plan, which will result in more sales for the company. So this is the objective. Obviously, the company will come to you and gives you the data and asks you for the marketing plan that will result in higher sales. Right. Obviously, now you should think. So what information would be useful for me to come up, me or the model, to come up with a better plan of spending money on these mediums for advertising. So we have to look for that information. So for example, so this is where you need to ask the questions, the right set of questions. So is there a relationship between advertising budget and sales? First question. So is there a relation between spending money on advertising and expecting more sales, right? If at all there is any, yes, we need to understand that relation and use it for increasing the sales. So most often what happens in machine learning, and particularly in academia, where I get some students who are interns, because I'm not guiding PhDs as of now, masters and BTech projects and internships I'm guiding at IIT Tirupati. So what I generally see is people, the enthusiastic BTechs come and they simply try to use the models to whatever problem at the hand. So for example, I'm working in a computer vision problem and I'll have some data sets to solve some tasks. And these people who are crazy about some of these techniques, deep learning, other AI techniques, they just want to, the focus is on the tools, not on the data, right? They want to use those techniques, they want to apply them to solve the problem. But basically, you need to really understand the data. So whatever problem at hand, you need to really see whether there is a relationship, particularly in this problem. If somebody comes to you with that, you have to understand, is there a relationship between these money spent on these advertising and sales? Yes, we believe that if you spend more, if you get more advertising, if you make the people talk more about this, obviously people will go to buy more. So this is the first step. You need to understand this. If this there is a relationship, then we can say yes, we can learn this relationship and understand it and use it for increasing the um, sales. And now we have to understand how strong is the relationship between advertising budget and scales, sorry, sales. So we need to really understand, is it a weak relationship or it is very strong? Basically, very strong means, if you really spend some money on some of these advertising, and if you see boost in the strong boost in the sales, then you can say it is very strong. If it is very weak, as for example, it may be difficult to see. Yeah, so in case of newspaper, if you see, it is not very steep. The line also, you can see the trend is not very steep, it is very weak. So that is what you need to understand, and you need to be able to answer at the end of this analysis also. Okay, so these are all very important steps which are generally missed by these new age um, machine learning practitioners. I just wanted to list down all of them, and so that it will be beneficial to think in a more organized fashion when you're attempting a problem. Otherwise, you will be spending your manpower and compute uh, in an unoptimized way, which is not suggested. So you need to optimize so that you need to make the right decisions and right steps. All right. So which media contribute to sales? So is it only one media? Is it all the media? Or how each of these medias are affecting, if at all they are affecting? And then how accurately can we estimate the effects of each of these medium? So yes, you will come up with, for example, you use the linear regression and you come up with some estimates, and you want to know how accurately these estimates work. So that also we can do using linear regression analysis. So in a way, you can think of these are capabilities of linear regression. All these questions can be answered using linear regression. And how accurately can we predict the future? Let us say you understood, you modeled these relationship between the sales and this advertising money, and how accurate you will be. Let us say you will come up with this predictor and give it to the company. He will ask, okay, I'm going to use this, and how accurate you are, so to predict. So I'm going to experiment, I'm going to believe you and then put some money, which according to your prediction, I should be seeing this, but how accurate you will be. So all these questions need to be answered, and linear regression also helps to answer these questions. And also finally, not very, yeah. So is the relationship linear? So yes. So we all know lines. These are very primitive things that primitive functions that can that we can easily understand. Line is basically, in 2D it will be uh, uh, yeah, how to describe a line. So yeah, it is a function. In 2D it will look like, with an intercept it will be going through y and all that. So is it really a linear relationship between these mediums and the cells? So all these things can be answered. And another important question generally asked by companies. So when we actually, do some research consultancy, the companies will pose very involved questions, because money is everything. So they ask very intriguing questions. For example, is there synergy among the advertising media? So there are three independent media we have seen, right? So if I want to, maximize the effect, can I exploit the synergy? Synergy means, when you apply two mediums simultaneously, the effect will be more than just adding both of them, right? So let us say spending 10,000 on TV will give you X, spending 10,000 on radio will give you Y. So if you spend 10,000 and 10,000 simultaneously, it will be more than X plus Y. So that is called synergy effect. So these kind of hidden things people ask. So linear regression does answer all these important questions. So that is what makes linear regression, one of the important tools. Okay. So now, having understood that it can answer a lot of questions, a lot of important questions, let us try to proceed. Okay, goals of this discussion, this 1 hour discussion, would be to develop basic understandings of linear regression. I want you to understand, how linear regression performs, how it accepts data and computes the parameters and all that. And we should be able to code it in Python. So it's a very simple, I don't want to trouble you, but at the same time, because, coding gives you a complete picture. Unless we do the model in Python, um, or any other platform like R. R is also a very good platform for statistics. So anyway, so I want you to do this. If possible, we do it in a hands-on fashion where I'll do it during the session itself. Okay. All right. Let's jump in without much delay. So what is linear regression? So basically, it is a predictor which predicts a quantitative response, as I was saying, response Y on the basis of a single predictor. If it is a simple linear regression, you will have only one input variable, and you are predicting a quantitative response Y, which is the dependent variable Y. So, and it assumes an approximate linear relationship between X and Y. So this is the key. The term linear in linear regression is coming from here, because it assumes a linear relationship between X and Y. So let us say I'll start with Y is approximately equal to beta 0 plus beta 1 times X. So if this is my assumption, you can think of this as a sales. Y becomes sales, and X can be the TV medium or radio medium or newspaper medium. So when you see this kind of a function approximation and try to estimate parameters, you see this is a linear regression. So people generally refer to this kind of a problem as regressing Y onto X. Y is the dependent and X is the independent. So when you say regressing Y onto X, you should infer that Y is the dependent variable and X is the independent variable. All right, so this is what I was saying. So in our example, sales can be the dependent variable, and TV means the amount spent on TV advertising. So if you just, replace those two, it becomes a practical problem. And let us see how we can, come up with more analysis. So let us try to have some terminology. So different people in, across community, they use different terminology. For example, as I was saying, some people refer Y as a dependent variable, some say outcome variable, some say response variable, because this is the response and these are the explanatory variables, right? So similarly, X, whatever the independent variable, you can call it as independent or predictor variable or explanatory variable. All these terms mean the same, right? And there are two important terms in the linear regression technique. So think of it as a line. So in that case, beta 0 become intercept, And intercept is basically the value of a function when the input is 0, right? If you remember the y-intercept and slope, if are given back in +1 and +2, I think. Yeah, maybe before. Yeah. So equation of a straight line when you are given y-intercept and y-intercept c and slope m, y is equal to mx plus c, right? So that is exactly what this is. Y is equal to mx, sorry, this is m and this is x and plus c. This is called intercept and this is called slope. And in more, machine learning terminology, you call them as model coefficients or parameters, because these are the parameters that define the linear relationship, how steep the relation is. Is it very strong or is it very weak? Things like that. So that is why these two are called model coefficients or model parameters. All right, so that's the terminology. Now, how to go about predicting actually? So let us say you come up with some parameter estimates, beta 0 and beta 1 hat. So in all the machine learning, not only in linear regression and in this class, but in general, when you see hat on top of a variable, what it means is it is estimated. So there is something beta, which is actual, and we're trying to estimate using some training data and some machine learning technique. And we ended up with beta 0 hat, which may be very close if the technique is really good and we have done a good job. In that case, we will be very close. Beta 0 hat will be very close to beta 0. But in general, beta 0 hat means estimate of beta 0. And y hat also similar. Y hat means it's the estimate of the value y, right? So in general, this is a notation followed in machine learning and statistics also. Yeah. So this is how one is going to use the estimated parameters beta 0 hat and beta 1 hat. If somebody gives you these two and how to apply them, because we assumed the linear relationship between x and y, we have to use the same line to get y from x. Once you get these two, it is straight away substituting value of x to get value of y. Again, y means y hat. All right. So now we know if the parameters are estimated, we know how to go about it, right? We know how to predict y. So first place, we need to estimate the coefficients. This is the crux of linear regression. This is the machine learning part. So let us see how it is done. So yeah, parameters are unknown. That is why we are estimating. So in general, you will start with okay. Let me just say, whenever there is an estimation, you have to have training data for estimation. Training data means some observations of the process. So the company will have, in this case, the company will have historic data every year, how much, or every month how much they are spending on TV advertising, radio advertising, and so on. And what is the impact of it? After spending that, how much of increase is there in the sales? How much of the sales have been, right? All those data will be there with the company. So this data is required to estimate the parameters. This is called training data. It is provided by the problem itself, the problem we are attempting, right? So it's a bivariate data because the relation is between two variables x1 and y1. And the generic thumb rule is more the data, better the estimation. So if there is a way to collect more data, which is reliable, noise free, so we should always accept data. So all this is data driven learning, right? So another important uh, notice to all the machine learning practitioners is to collect as much data as possible. If you have better data, if you have more data, your machine learning techniques will perform better. All your estimates will be closer. The errors you incur will be smaller. Of course, the data has to be representative and clean. So if there is noise involved, obviously we have to minimize the noise involved in the data in the collection process. But general thumb rule is accept as much data as possible. Yeah, in particularly, if you go towards deep learning, artificial neural networks that are very uh, data hungry, you need to have a lot of data. That is why data sets like ImageNet and all, they involve millions of images. All right. So the main ingredient for estimating the parameters of linear regression or any machine learning technique is the data. So we need to have carefully collected data as well. All right, once we have the data, what we need to do is we need to fit the variables beta naught hat and beta 1 hat, right? Let us say xi is one particular sample, the input of that sample, and yi is the corresponding output sample. So fitting means, substituting xi and getting yi. So we don't know beta, what should be the value of beta naught and beta 1 hat, right? Obviously it is going to be very different from, if you substitute some other values of beta naught and beta 1, the yi estimate will be different from yi, right? But what we should do is we need to bring yi hat to be closer to yi, right? That is when we say the model is fitting to the data, correctly fitting to the data, right? So this you can really understand or relate with the objective function in machine learning, right? So what the objective function should do, or the cost function should do, is minimize or bring the estimates close to the actual value, right? So this is the computed estimated value. It may not be close to yi. Yi is the actual value we observed for xi. So it may be approximately, but we want them to be really, really close. So how to measure this closeness is the um, objective function, or cost function. Generally, it is referred to as objective function. All right. So this will have a different form based on the relation. For example, if it is very complex relation, you may not be able to see this kind of a simple explanation. For example, if it is a linear neural network, it's neural network which accepts xi and gives yi. It may not be, a linear relationship. So although linear relations can also be learned using neural network, it will be more sophisticated in general. In that case also, we need to bring down the estimates close to the actual values. How do we do that? So this is what the discrepancy. Discrepancy means the difference between the actual value yi and the estimated value yi hat. So ideally what we want is these two to be equal and ei to be 0, which may not be possible because the data may not be actually linear, or there may be noise, things like that. The complexity of the problem and all that will give you non-zero residual or error. So these terms are generally referred to as either error or residual, which is this difference between the actual value and the predicted value. And we want to minimize this value. So that is the objective while estimating the parameters, right? How do we go about? So if you just simply add all of these things, for example, you will have 200 samples given as a training data. You will be given xi yi pairs, 200 such pairs. So you compute this and go on adding this uh, discrepancy or residual, because this can be both positive and negative, right? If you just go on adding, they may cancel out. Positive values and negative values may cancel out, and it may result in 0, thinking that the model is fitting correctly. But that's not the actual thing happening, right? Because of the signs they are canceling. So general in all these cases, generally what we do is we take the squared sum. So it is also very fundamental. So sometimes you miss this point. That's why I want to emphasize. So why we take squared error all the time is because it will give you the representative error. If you simply add these things, things may be really messed up. So you go for RSS, which is called residual sum of squares. So this is sum of squares. Each of the quantity is residual. It is called, that's why, RSS, residual sum of squares. So if you expand, it looks like this: actual yi minus the estimated yi, square of it, taken over all the training data, 1, 2, 3, and so on, n. So this is what we do. So we have to minimize the discrepancy and compute the RSS. So now, all right, okay, yeah. So I just want to visualize what we are minimizing actually. So if you see diagrammatically, so let us say the same problem, which is spending on TV advertising and predicting the sales of the product. So each of these dots is the actual data, and the blue line is the line, which is beta 0 plus beta 0 hat plus beta 1x. So that is the line which is shown in the blue color, and the individual points are shown in the red dots. And the error is basically the line joining, the gray line joining the point to the um, line, blue line. Blue line is the regression line. Y hat is equal to beta naught hat plus beta 1 hat x. So these are all the errors. These are all the residuals. All that we are doing is we are squaring these residuals and summing. So, so I just want to give an interpretation of the RSS, the residual sum of squares. So this is how the residual sum of square looks in a diagram, onto a line, register line. All right. Now we're actually going for the minimization. So basically, we started with the objective, which is minimizing the discrepancy between y hat and y, and this is how it looks like. And now how to go about it. So just go to the +1 +2 calculus, where you will be given a function and we want to find where the maxima is occurring, or where the minima is occurring. So whenever there is a maxima or minima, you clearly see the gradient of that function becomes 0, right? So so that is what we are going to do now also. We have the loss function or the objective function, which is this. And now we want to find out the optimal values of beta 0 and beta 1, where this becomes minimum, right? We need to find such beta naught and beta 1, where this RSS is minimum, right? The discrepancy between the predicted and the actual value should be minimum, right? So that is what is happening. I hope you see what is being happening. Basically, there are two parameters, beta naught and beta 1. L or the RSS is the function of beta naught and beta 1. We want to find suitable values for them so that this loss is minimized. So I'm applying that calculus where I, I find the partial derivative of this loss with respect to the beta 0, because I want to find both beta 0 and beta 1. Once I find with beta 0, and another time I'll find with beta 1, and make it equal to 0, right? So this is simple minimum maximum I'm computing, where the differential partial derivative I'm making it equal to 0. So that is why at the minimal point you will see gradient to be 0. The tangent will be parallel to the x-axis, right? So I'm just giving you a complete picture how to actually compute the estimates of these parameters. So you don't need to do all these things. The formula, once it is understood how we obtain, we can use this formula directly. So I just want to give you that mathematical background also, just in case. So all right. So if you simply follow the steps, which is very straightforward. So because it is in the form of x squared, derivative will be 2 times x, and I'm making it equal to 0. And there is a summation. And if you just do separation into left hand side and right hand side, you will just do 1 or 2 steps. You will end up with beta 0 hat is equal to y bar minus beta 1 times x bar. Y bar is the mean of y. So you will have small n number of samples, both xi and yi. So if you take the mean of all those yi's, it will be y bar. And if you similarly take the mean of x, it will be x bar. And beta 1 is the optimal beta 1. How you have to find? Similar way, dou L by dou beta 1, if you make it equal to 0, you will find the expression for beta 1. And both of them look like this. So beta naught hat, the optimal value looks like this, and beta 1 hat looks like this. So this is over all the training data. You are minimizing the correlation. Sorry, you are computing the correlation, x minus x bar, y minus y bar divided by variance, x minus x bar squared. All right, so this is the whole point of linear regression. So it may not be. This is the very important point, because you need the estimates, which are beta 0 hat and beta 1 hat. From the training data, you can compute. Remember, more the training data, better the estimates, and um, noise free. If you have representative data, clear data, it also gives you better parameters where the residual is minimal, where it will be controllable within the bounds. All right. So let us say we obtained beta 0 in the TV problem, the TV and sales problem. We found out beta 0 hat as 7.03 and beta 1 hat as 0.0475. Right. So if you remember, there were a set of questions. So we want to understand, or we want to be able to answer um, how strong these relations are between um, the money spent on TV and the sales of the product. So one of the questions was that. So not only to understand, whether it is linear, whether they are dependent, how accurate these estimates are, all those questions can be answered. But let us see how to understand the strength of the relationship between the TV advertising and the sales. So what this means is, so once you do have these parameters, now you can say an addition of $1,000 that is spent on TV advertising is associated with selling approximately 47 and a half additional units of the product. So that is what the slope tells us, right? Slope means, if you have, dy by dx, right? So a change in x will cause how much change in y. So that is how you should understand the slope. So now if the company asks you, if I want to increase, let us say 100 additional units in the next month, how much I have to spend on the TV advertising? So because now you know the relationship, you can answer that question. You can suggest the company to spend accordingly, right? So there may be a lot of questions. If I want to spend only this much on my TV advertising, how many products I can expect to um, sell more? So all these questions are related. So this is what the companies actually want to know, how much they can spend. They will have limited budget, or they want to maximize the effect of putting money. So they want to do all these calculations, how much I need to spend to increase this many products, or if I have only this much, how much I can improve. All these things will be answered. So that is the power of linear regression. So this is very simple actually. So there are a lot of concepts involved on top of whatever we have done so far, right? So I just wanted to give you one possibility, show you one of these questions, how important, how powerful this tool is. So you can apply it on any of the research problems also to understand this kind of strong or weak relationship between the predictors and the predictor values, right? Yeah, so there are a lot of concepts. For example, you can think of the optimization. So in this case, beta 0 and beta 1 are two parameters. That is why the RSS is a function of two. RSS means the loss, the residual sum of residual squares, right? So it looks like this. So we need to hit that minimal point. I was telling you, right? Because the function um, will be minimal at the local minima or global minima, where you have to find out the um, gradient and make it equal to 0. Dou L by dou beta not equal to 0 at this point in red, which is shown in red here and here. So basically the left hand side is the um, so what is it called, level planes. Level planes means, if you imagine this 3D plot and then cut in horizontal direction, uh, so you will see these circles, right? You can imagine circles when you cut the u-shaped cylindrical shape. You can cut and get these level sets. Level sets means, these are points that have equal cost, equal RSS. For this, for example, here in this circle you'll have 3, in this circle 2.5, and so on. Yeah, so this is displaying how the loss is, varying with respect to beta 0 and beta 1. And clearly at the estimated points of 7.03 and 0.04, the loss is minimal. So that is what is happening. This is actually output trained on the real data. That is why you see at these parameters, the loss is very minimal. So this is also very important. You need to, as a machine learning practitioner, we need to use visualization as much as possible. We need to uh, plot and really see the surface, how in 2D and 3D you can do, but if it is higher dimensions, obviously we cannot do. But these small or simpler problems also help you get insights that help you solve the bigger problems. All right, so this is loss visualization. So this is very important in complex problems also. All right, so what we have seen so far is a simple linear regression, where basically simple because there is only one independent variable. So although there were TV, radio, and newspaper, we were considering one at a time. That is why it is simple. So that is why we call it simple. But obviously multiple linear regression is also possible, where more
This
than one,
conference will now be recorded.
right? So where more than one independent variable can also be included. For example, here you see n number of independent variables x1, x2, and so on, xn are considered for predicting y. In that case, you will have n plus 1 variables to estimate, right? So you need to estimate beta 0, beta 1, and so on, beta n. So it is also linear. Clearly, there is no square or any logarithm or any polynomial sort of a relation between x and y. It is simply linear. You can clearly see y is equal to intercept and the slopes in different predictor directions. So I'm not going into the details of multiple linear regression. This is also possible, and people do use this to understand synergy and how to invest carefully simultaneously in let us say TV and newspaper or TV and radio. Similarly, combinations and all that you can understand. All right, so I strongly want the participants also to take this opportunity to go ahead and code. So if you want, I can wait as you go code also. But if you prefer, I'll share this notebook, and I'll go through the step-by-step code so that you will see what we have discussed in the slides. Here also you can clearly see how we are going to estimate from training data and compute the parameters b1, beta 1, and beta 0, and even predict also. After that, once we get the beta 1 hat and beta naught hat, we will take any x and give y, corresponding y, right? All right, so it may not be very complicated thing, but it gives you, implementation in machine learning is very powerful. It's equally important to knowing the concepts, if not more. So I see a lot of interns who apply to internships also do this. They go through a lot of online courses nowadays. Thanks to Coursera and MOOCs, a lot of NPTEL, SWAYAM, a lot of courses are available. People do learn enthusiastically, but what they lack is implementation. See, it's an applied field, so knowing the stuff is only half good or less maybe. So what makes the right attitude in machine learning is the ability to implement. However small the project is, however small the problem is, you need to have the hands-on experience, right? Industry actually look for a quick prototyping. Quick prototyping means, having an idea is not good enough. Making it as a product, how quickly you can turn your ideas into products is what is important in industry. So I strongly encourage or suggest you to also develop such ability. Of course, it takes some disciplined um, practice. So yeah, you can start with this linear regression example where Python nowadays is very strong, becoming very very strong for machine learning and AI, with a lot of deep learning libraries getting added every day. So I strongly suggest people, all the participants to start looking for such experiences. Such assignments help you a long way, right? So this is what we do at IT Tirupati also. I mean, even before. So we try to understand the concepts and immediately we have to work it out in code and develop models and try to see all this theory part in action, right? So yeah, so there are a lot of platforms. So you can visit Kaggle for more complicated machine learning problems, but all the textbooks are also good enough to start with. So either R or Python. So you can use both of them or any one of them. So for long term, I would suggest Python. So go for Python. There are a lot of online forums also where you can post any question. If you are not able to solve some of the issues, if you are not able to use the constructs of Python according to your utility, you can always post in online forums, right? From Stack Overflow all the way to PyTorch or TensorFlow. Forums are also here, there to help. So I learned myself that way also. So I strongly advise you. Let us now go take a look at this simple bunch of code. So these are some libraries. Everybody. So we start with importing the required libraries. So pandas is a statistics library. So in Python, and NumPy is also number Python. So basically, it allows to hold the data in matrices and operate on them and all that. So matplotlib is basically for plotting. We need to visualize data. So it is very rich library. You can do a lot of visualizations in 2D and 3D also. So yeah, in image processing also, a lot of people use matplotlib. Of course, there are dedicated image processing libraries, but simultaneously you can use in Python. All right. So what we want to do now is we will have some x and we will have the corresponding y. Obviously, you need to have a linear, approximately linear relationship between x and y. So only then, so you remember, we need to ask that question: is the relationship linear or close to linear? Only then we will go for linear regression. If it is not linear, and if somebody or some knowledge tells you it is let us say quadratic or any other complicated function, we know right from the beginning that linear approximation will cause you more errors, right? So we need to understand the relation, and if you have sufficient evidence that it may be linear, then you should go for it, right? So in this case, because I don't have that TV data, what I'm doing here is I am computing, or I'm using the data generated like this. You can see x is equal to 2.5 times x, sorry. So you can think of this as a uh, random sampling of data. So basically, I am having x coordinates, 100 x coordinates, right? So this is my x coordinate. So I'm just randomly generating. So there can be different ways of generating x. So I'm just taking, basically, you can think of it as a sampling a Gaussian with mu is equal to 1.5 and sigma squared is equal to 2.5 square, right? So this is randomly generating x's. Okay. So now this is my approximate linear function, 2 plus 0.3 times x. Okay, EPS is basically some error. It need not be, exactly linear, right? When I generate x comma y, it may be, there may be some errors, or there may be some, the function need not be exactly linear. Maybe it is close to linear. This epsilon or this noise is basically, which is uncontrollable. It is independent of x, and it becomes from sample to sample, it may be different. If it is also dependent on x, it will also go into this coefficient, right? 0.3 plus epsilon times x or something. Because it is independent of x only, we pushed it away from 0.3 times x. Yeah. So if it is confusing, think of it as um, some uncontrollable error, or the function we are estimating may not be linear all the time, right? If it is exactly linear, yes, EPS is 0, but it need not be exactly 0. That is why we are including that uncontrollable parameter EPS. All right, now this is how I generate y, right? I substitute x here, 2 plus 0.3 times x becomes y. Now I have x and y. All that we need to do is, as if we behave as if we got x and y, we don't know how the y's are generated. Okay, so because we don't have the company coming to us and giving the data, I myself have generated some data x and y. Okay, so yeah, there is pandas data frame, which is basically to access data very easily. So if you think of it as a simple dictionary where you have both x and the label y in rows fashion. And if you say df dot head, it will give top 5, tail, it will give final 5, and so on. You can access any individual data samples also. So for example, let me run this. So this is not running on my computer. Colab is a Google Cloud facility. This is also another opportunity for a lot of us, basically, who don't have much of compute facility. If you simply have a good internet speed, I think this is good enough. Where Google in a cloud gives you all these libraries. You can just start coding in a drive, in a Google Drive file. as an IPython notebook. Okay, I believe most of you already know, but in case you are not aware of it, please use this facility where it's called Colab, collaborative lab for Colab. All right. So the first step is basically creating data because not no company is coming to us for consulting, right? That's why I created my own data. And now, if you remember, the second step is estimating. So let me go back. So these are our estimates. Given the data X and Y, we need to find out the parameters, estimate the parameters beta 0 hat and beta 1 hat. That's the first step. So how? I showed you how we can derive. Now we don't need to do all that. We have formula directly for beta 0 and beta 1 hats. So you can simply use this formula and compute them. So here you can see I have computed x mean, that is x bar, and y bar, which is basically mean of all the x's, mean of all the y's. So these are simple commands you can simply use. And then now we have to have the x minus x mean, y minus y mean in the numerator term. So let me just revisit. So x minus x mean, y minus y mean, summation of this product over all the training samples divided by x minus x bar squared. This also summation over all the training samples. So that is what I'm realizing here. Yeah. So x minus x mean, y minus y mean. This is x minus x mean squared. So beta is beta 1 hat in the formula in the slides. So numerator dot sum, if you see this one, so this dot sum is doing the summation. Here also dot sum is doing the summation. So we just put in this data for computing beta and alpha. So alpha means beta 0 hat in the slides. I just named them like that, but you can always do beta 1 and beta naught here. All right, alpha form beta 0 naught, beta 0 hat formula is y bar minus beta 1 times x bar. So let me just revisit quickly. Y bar minus beta 1 times x bar. I'm just realizing that here. So if you just compute that, you will have 2.00, 0.323. If you see, if you go back, so alpha is 2 and beta is 0.3. And there is some epsilon error, which makes it not exactly linear, but close to linear, right? So our estimated parameters, so 2.2 and 0.3, right? Yeah, so 2 and 0.322. So there is a lot of error here because 0.3 to 0.322 is a little more than designed. So for example, if you have more data, so you can take more data here and then start, let us say 500. I'm doing 500 here just to make sure, what happens if we have more data. So I have now 500 data. I'm computing x mean, y mean. Yeah. So now this is what the estimated parameters are. Yeah. If you have, yeah, I lost the original data. Otherwise, I would have computed the error in the data. What is the relative error from 2 and 0.3, right? So that way you can see. I mean, not in one experiment. Obviously, you have to do a lot of experiments and try to see. With more data, you will see more closer approximations to the data. And if the data is small, let us say you only have 50 or even smaller, 10. Okay, so somebody gave you very less data and asked to predict the parameters. Yeah, I mean, this time we got lucky. The errors are not very big, so it need not be the case. Generally, if it's less data, you will see more error in the estimation. All right, yeah. So you can work out. You can try not only this after going for multiple regression. Uh, the formula will be very similar, but a little more complicated. And I'll provide you references how to go about it now. All right. So now let us say we estimated these parameters. Now what we need to plot them and predict. So predict means basically applying the beta naught and beta 1 on the data. So let us say I'm analyzing the training data itself. There is no test data. but I want to analyze the training data itself to understand how well the predictions are. So I'm plotting. So plotting basically is applying the x and getting y and then scatter plot. So the red dots are basically um the scatter plot shows the actual data which is used for training, and y predicted is putting the x in the beta naught and beta 1 formula. So this line represents the prediction, right? So you can see, because the data itself was approximately linear, our fit is really good, right? So this is what the question, one of the questions initially we asked, whether the relation is going to be approximately linear. Yes, if yes, linear regression is the tool. Even if you suspect, you don't need to really know. Obviously, it is not practical to know. In this case, we know the data because we only generate it. But if it is actual data coming from a physical process, we don't have any clue. But there might be some domain knowledge which may suggest us to think or believe that the relation might be close to linear. So in that case, yes, you can go for linear regression, collect the data and put into the estimates formula and estimate beta 1 and beta 0, and now try to see how well the approximation is or how poor the approximation is, depending upon the data, quality of the data, and the relation, how closely it is to the linear, or how far away from it is from the linear. So all these things really affect. And once you have these parameters, you can answer some of these questions. As I said, um, if I want to increase the y by this many, how much I need to spend on x, how much I need to improve x, things like that. If I have budget of this much x, how much I can see, uh, how much change in y I can see, and all those things. That is only some of the possible questions. Right now, you can ask a lot of questions. If you are really into statistics and research, you can go about confidence intervals. Confidence intervals means how confident that yeah, your predictions are, and intervals means with a probability specifying these predictions, not just one value. Instead of one value, you will give a range with associated confidence, right? So all these things are possible. um, yeah, that is why linear regression establishes itself as the one of the fundamental building blocks of statistical learning, actually. So statistical learning starts with linear regression, although whatever limitations of linear regression. So let us discuss, because now we have arrived at a point where we can discuss the limitations, right? So by now you should be able to understand the limitations, right? So the important limitation here is basically, if the relation between the independent and dependent variables is not close to linear, then you are supposed to get huge errors. You will incur um, big errors which may make the technique itself not usable, right? But the thing is, um, it's a starting point when you don't have any clue. For example, most likely you will not have any idea about the relationship, right, between x and y. So for example, in the same example, what we have seen, sales and the advertising, if you don't have the data visualized, or even if you have the data visualized, you know the simplest of all the functions is a line. So obviously it will have a strong baseline, you can use it. But depending upon the deviation of the actual function from the linear function, your errors will increase, your estimates will go poor. So that is the main thing you have to keep in mind. But nevertheless, the uh, linear regression, particularly in the business world and in the industry world, it acts like a strong baseline. Like baseline means, whatever you develop using your intelligent machine learning and deep learning and whatever you technique you use, it has to beat, it has to outperform these models. Because if you don't have the benchmarks, we don't know how good or how bad the actual technique or whatever you implement is working, right? It's like, think of a random guess. If there are 10 categories, if you randomly assign labels, or if you assign same label for all the classes, you will be getting 1 by 10, which is 10% accuracy, right? That's a stupid baseline. Stupid baseline because you're actually not using any intelligence there, right? On top of those stupid baseline, I'm not talking about, I'm talking about the worst case of linear regression, right? So that itself is better than the stupid baselines. But generally, it is not that bad. So in my experience and in a lot of other people's experience, particularly when it comes to, um, um, so time sensitive business worlds, we need, uh, better than stupid estimates as baseline. So that is where linear regressions and also it is very simple. Computationally, it is not very expensive. It doesn't need to store data. All that you need to store is the parameters. Once you have the training data collected, you apply these closed form solutions and get beta naught and beta one, and that itself is good enough, right? Computationally, very effective to predict. Applying only alpha x plus beta or beta x plus alpha. So that is why it is used, inculcated in several applications. All right. So I hope I will be able to share this um, simple notebook also through Dr. Ravi Chandra. I'll be able to share them. All right. So let us have some Q&A if you have any for the last 10 minutes. So that means I'm almost done. Right. So yes, yeah, it can be time for discussion.
Dear participants, please come forward for interaction. We have 10 more minutes.
So I planned it to be, an interactive session. If you want to, I can keep the screen and you can also, do it now so that if you have any errors, I can help you resolving. Or else if you want to take it up offline, anyway, this thing will be shared with you, so you can take it up. Yeah, in the second session, which is for logistic regression, which is basically classification. So where you assign labels for the input X instead of having a quantitative response. So that also I have a similar IPython activity. Yeah, so you can decide among you. If you want it to be, sorry, if you want it to be interactive, you can do it like that. Or else, if you want to simply me to walk you through the code, that also I can do. That is a little complicated module, so anything is fine. Yeah. Yes, I'll be able to share. Let me see. There was some message. Right. Yeah.
Participants, you can even drop your queries in the text box. Else you can unmute your devices and speak to sir.
Yeah, I've shared both the files.
Sir, have you shared HTTP1 also, sir?
I'll share that. Yeah.
Yes, sir. Thank you, sir.
No. That may not be here. Okay.
We expect participants to participate in interaction.
Sir.
Good evening. Yes, ma'am.
Yeah,
Vilaki,
please.
ma'am. Go on, ma'am.
Yes, sir. You told that you need to increase the data size in the data set, na, sir. Is there any limit? Is there for setting a training data set and testing data set, sir?
Yeah, that's a difficult question. So general idea is to have more, but how many is more, how many is less? We cannot quantitatively say that. But only thing is, the error estimates get poorer with less data. It depends. Basically, it depends on the complexity of the problem. Um, and by complexity, I mean, what is the EPS value? How closely the actual function is to the linear um, function, all that. So if it is decently close, a good amount of this thing is okay. But
Okay.
but if it is little far away, even with increase in the data, we may not be able to improve our estimates because the nature of the function itself is little away from being linear, right? So, but in general, to precisely answer your question, uh, we cannot have. Let me correct myself. So it's very challenging to come up with quantitative size of the data set. So generally in machine learning, better, bigger is the better. So bigger again. So we cannot say how much is bigger. Depending on the complexity and experience, we know how much is bigger and all. Yeah.
Sir, if I increase the data set, again I am facing one problem is it will take more time, sir. For example, if I'm going for prediction process and all, if I use
Hmm?
LSTM, you know that LSTM already took more amount of data, more time for generating the model, na, sir, with the training process
Yeah,
itself. So if I,
true.
yeah, that trade-off also I need to take care of that, sir. That's why I'm asking, sir.
Yeah. So this is very practical. So generally, when we use RNNs, particularly LSTMs, yeah.
Hmm.
So we need to have good compute, like GPU and all. So uh, yeah. So most unfortunately, the research in this area is governed by having compute now. So that is required. Uh, yeah. If you don't have that, we need to carefully pick the data size also. Yeah. So that is correct. So it is a cat and mouse problem. If you have more data, you need to have more compute. If you don't have that, we need to reduce the size here. Yeah. So that is correct. But if you have any domain knowledge, you can carefully pick the right data so that even if you're using small training data, it is okay. So that is where domain knowledge comes. So if you know the problem very well, and if you can, somehow understand which data is good, which data is to be given more importance, restrict your analysis to only that data.
Okay, sir. Thank you, sir.
No problem.
Uh, Sir, good evening, sir. I'm audible.
Good evening. Yes, sir, I can hear you.
Sir, there are some regression model I have seen in some literatures,
Okay.
like the multi-kernel regression model. Sir, these, how they are different from the linear regression and multiple linear regression?
So multi-kernel, can you explain more details? Like, so the function is not linear. Clearly, multi-kernel means you have a complicated function, like some sort of a non-linear embedding is happening. But Yeah, I need more details. Like, can you tell me what the function looks like? Of course, multi means there are multiple variables involved. That is clear. Kernel means some sort of complicated function is being involved. Yeah. So what I mean to say is you can have complex relations also modeled, not only the linear, and it can involve multiple variables, independent variables, not only one independent variable. So depending upon the domain knowledge and the nature of the problem, we can inculcate such a complex function. For example, polynomial I can use, or I can use gradient functions where very complicated, sophisticated function is being used for approximate the relation between x and y, the x's and y. So yeah, I think it looks very advanced with more and more complex relations between x and y modeled.
It means it is the one of the type of a regression model, just like a linear regression, multiple regression, then a multi-kernel linear regression, but the multi-kernel regression model, and the one of the model is a Gaussian process regression and multiple approach. Sir, actually, I have seen these type of regression model in the literature.
Okay. So from my understanding, what it looks like, so they are all extensions of these things, but in a non-linear fashion, because you're saying functions that are not linear, right? So that is why I'm assuming, I might be wrong here, but I haven't come across such models. Yeah. So can you, if it is possible, can you share the links or any suitable things? I can take it immediately, and when we meet the day after tomorrow, I can quickly spend some time.
Sure, sir. I have shared the papers link where I have found the these names.
You're Praveen Kumar, is it?
Yes, sir. Praveen Kumar, sir.
Can you please share it again? I don't see it here.
Sir, actually, right now I'm logging with my phone. There is some problem in my laptop.
Okay, okay. So
Not
you can
possible
find
for
my
me right
mail. No problem. You can find my mail ID now, so you can send it to that. I'll take a look.
Okay. Okay, sir. Okay. Okay.
Yeah. So my website have more details about reaching me. So please feel free to do that.
Okay. Okay, sir. Okay.
I think Praveen sir got his answer.
Yeah. Thank you, sir. Thank you, sir.
No, welcome. You're welcome. No problem.
Sir, I have one question. This gradient descent algorithm, by default, it will work when we write the code in Python, or any library to be included, sir, for this linear regression?
So for linear regression, the solutions are in closed form. Closed form means you will have a formula. If you substitute in the formula, you will get beta naught and beta 1. But for more complex problems, that is not possible. That is when we use gradient descent. So for gradient descent, you need to use some libraries because it is an optimization function. So we need to use optimization library. For example, PyTorch, TensorFlow. These are all libraries which can give you the modules which can implement the gradient descent algorithm in your problem. Okay, so yeah, so there are libraries. You need access to those libraries. So you can import PyTorch and start using those stochastic gradient descent, all these methods. Yeah. So for linear regression, please observe the difference. It is possible to give closed form solutions. That means it is not iterative. It is a numerical method. If you simply put in values in the formula, you will get the answers. But neural networks and other complicated optimizations, you cannot do that. You can get the parameters in single shot. That is why you have to do it iterative optimization. So that is where you need gradient descent.
Okay, we can't. No need to use this gradient descent in linear regression, sir.
Yes, no need to use, because if you see, are you able to see my screen, sir?
Sir, only you are visible to us, sir.
Okay. So let me share. So if you see beta 1 hat and beta naught hat, you have closed form solutions. That means if you have these right hand side values, you put in and you get beta 1, beta naught. Right. That is where you don't need gradient descent. So here you simply have gradient descent is kind of a numerical method where you improve the solution step by step, right?
Yes, sir.
Yeah, so you don't need to solve this problem.
Okay, sir. Thank you, sir.
No problem. Yes, I will share. I will share. Yeah. All right. So if you don't mind, I have another BTP meeting in Tirupati at
Yes, sir.
3:30. I'll stop
Yes, sir.
here.
Yes, sir. Yes, sir. Thank you, sir.
Yeah.
Thank you
Thank you
very
all.
much, sir.
No problem. Thank you.
Thank you, participants. That was a wonderful session. We request you to have rest for the day. Come back tomorrow at 9:45 a.m. We will be waiting here. Thank you very much, Professor. Attendance links, feedback link has been shared to everyone. Actually, both are the same. Attendance and feedback is the same. Has been shared in the Meet, in the group, in the WhatsApp groups also. Please make yourself comfortable to fill the links. Thank you, everyone.
This conference is no longer being recorded.